Welcome to the course of analysis of several variable. So in this lecture we will start module 4, which is partial derivative and directional derivative of several variable functions. And we will start with the partial derivative. So section 4.1 is partial derivative of several variable functions. So let's define the partial derivative. Let omega be an open in Rn, and a1 a2 an is in omega, and then we have a function f is from omega to Rm. Then we have k equal 1 to n. We say that f is partial derivative with respect to x n, or you can say xk at a if we have the limit x tends to ak, the function f a1 a2 xk an minus the point where we are taking the partial derivative in x minus ak. This exists in Rm. So if this limit exists in the Rm, because f is a function from Rn to Rm, so this f a and this point will go to Rm. So therefore, if this limit exists in Rm, then we say that f has a partial derivative with respect to xk, the kth variable. We denote this limit by del f del xk at the point A, or f suffix xk at the point A, and some cases also dxk f a. Different books or different manuals have different notation. Well, so in this example, we are going to check if the given function is partially differentiable at the point a is equal 0, 1, and with respect to y at the point 1 minus 1. Let's see what is the function. The function is given as is defined from R2 to R, and given is like this: fxy equal xq minus 2yq over x square plus 5y square, and xy not equal 0, and 0 when xy equal 0. Now we'll check it that it is differentiable at partial derivative exists at 0, 0 and 1 minus. So before doing that, we just take it the definitions. We will recall the definition. So fxab, this can be written as limit h tends to 0, a plus hb minus f of ab over h. Same way, fyab is equal ab plus h minus f of b over h. So this is partial derivative at the point a, b. So now in this case it is 0, 0. So a equals 0, b equal 0. So fx 0, 0. So f of a is 0 minus f of 0, 0 over h. So if you see the function, so this will become h to the power 3 over h square minus 0 over h. And then we simplify it, you will get the value is 1. So the partial derivative of f at the point 0, 0 is 1. Now let's check the partial derivative with respect to y. So again, f y 0h is equal to f limit h tends to 0, f 0h minus f 0, 0 over h. So now in this case, what we'll have from the given functions, we'll have here f0h is equal minus 2h to the power 3 over 5h square. F0, 0 is 0, and then h. So if you simplify it, you will get it minus 2h to the power 3 over 5h to the power 3. So h to the power 3, h to the power 3 will cancel out, so it will be minus 2 over 5. So finally we have the conclusion that the partial derivative with respect to xy exists at 0, 0. Now the second part is, it says that we have to calculate fy1 minus 1. So here we are trying to define a little bit a different way. So this can be written as limit y tends to b f of ay minus f of ab over y minus b. So thus f of 1 minus 1. So this will be a equal 1, b equal minus 1. So this will gives you 1y minus f1 minus 1, and denominator is y plus 1, and the limit is goes to y tends to minus 1. Then we systematically solve it. F in the f, just replace x by 1 and y as it is. So you will get 1 minus 2y to the power 3, 1 plus 5y square, and then this one will become 1 plus 2, 1 plus 5. That means it is 3 over 6, so 1 over 2. And then we further simplify it. So you will get it in this form: 2, 1 minus 2y to the power 3 minus 1 plus 5y square, and denominator is like this. Now we'll try to get the limit for this. So for that we separate it, that which is not a problem in the denominator. So this part we separate it, and here is a problem. We have y tends to minus 1, this denominator will become 0. So we'll try to solve it in different way. So here we got a directly limit. Here we got a directly limit from this part, and then this remaining part after simplifications will have this part. So clearly you will see that this is 0 over 0. So we can apply L'Hopital rule, and then we'll have this form: 1 over 12, and then it will be minus 10y minus 12y square over 1. And then put y equal minus 1 and simplify it. You will get the answer as minus 1 over 6. Okay, now we have few notes. Note 1 is that if we take x equal this from Rn, and then partial derivative of f with respect to the variable xk at the point A can be written like this formula. This is standard formula. Okay. So now we'll substitute it here: xk minus ak equal t. So this implies xk equal ak plus t. So t is just a variable. You can substitute any other variable also. So now we'll put it x k equal ak plus t, and then replace it in this equation. So after that, what we'll get? The derivative of f with respect to xk at the point A is equal, this x will replace by ak plus t. Okay, so remaining is same. Then we will get it here. So now our task is to write this part. So this part can be written as a1, a2, ak, an plus t 0, 0, 1, 0, where 1 is the kth entry of the vector. So therefore, we got it here: a plus t ek. So therefore, this vector can be replaced by short form a plus t ek. So we can rewrite it, this vector, as limit t tends to 0 f a plus t ek minus f a over t. Okay. Now we have the second node. In this node, we will take the point A and then partial derivative of f with respect to xk at the point A. So then we calculate all this. Means to whom, with respect to which variable you are doing derivative, you have to keep that as a variable. Other point you can substitute it the value of the point. Means in this case x equal ak, means x1 is equal a1 a2 ak an, x2 is equal a2 a1 a2 xk plus 1 xn. Okay, now we have note 3. This says that if the function f, capital F, has a component of functions f1, f2, fn, then the partial derivative of capital F with respect to xk exists if and only if all f1, f2, fn have a partial derivative with respect to xk. Note 4 is that if partial derivative belongs to Rm, then f dash a is linear from Rm to Rm. Now with this we have examples here that find fx230 partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to g, while f of xyg is this function. So this is easy function, you can solve it directly, but here I will give you one technique to solve it uh, and convert it almost the ordinary derivative. So in this case what we have, fx230, we can write it del x of fx30. So if you remember, we have a note in this slide that the to whom with respect to we have to take the derivative, we can keep this as a constant. Now what will happen, that fx30, so we'll substitute it in the function, and then we will get it del x, x e to the power 3 multiply 0 sine x dot 3 dot 0. So therefore we got it here. This is become x and this is 0. So therefore we will get del x, x 0, and now partial derivative of x is 1, so we will get it 1 0. Now this is partial derivative with respect to x. Now what about with respect to y and with respect to g? Now with respect to y, again we substitute the value of x, value of z, and y is constant, so it is as it is. So therefore, if we take the derivative here, so this is we have to calculate at the point y equal 3. Now here you will see that f2y0, we have this function, so we will put it x equal to here, y equal as it is, and g is equal 0. So therefore you will get it here x e to the power 0, x e to the power y 0. So and here it will get it sine 2 y 0. So we got this point here, that del y to 0, which is gives us 0 0. So this is the answer. Now move to the next question. Next part of this, fg230. Now we have on g. So this is now given as del g of 2 e to the power 3z sine 6z. Because if we put 230 here, so you will get it here. X is 2, y is 3. So it will be 2 e to the power 3z. And then here it is, you have sine x is 2, y is 3, 6g. Now if we take the derivative here, so this will give you 6 e to the power 3z, and this is 6 cosine 6z. So after simplifications, putting the value of g equals 0, you will get in this form 6 e to the power 0, comma 6 cosine 0. So the final answer is 6 6. Let omega be open in Rn and A is a point in the omega, and we have a function f is from omega to Rm, and we assume that this is a differentiable function at A. Then all the partial derivative of f at the point A exist. Means you have here, as it is from Rn, so we have n variable. So f has an n variable. So x1, x2, and xn, we are denoting those variables. So therefore, the function f is partially differentiable with respect to each variable at the point A. And further, we have the partial derivative with respect to a particular variable k. So xk, we will have f dash a e k. So while ek is the unit vector 0, 0, 1, 0, 0. So this is the kth entry. And for all h belongs to Rn, we can write this as f dash ah can be written as the partial derivative with respect to x1, h1, with respect to x2 multiply h2, and with respect to xn multiply hn, and which can be formulated by this summation. So now we are going to prove this theorem. Since the function is differentiable at a, from the definition of differentiability, there exists r greater than 0 such that f of a plus h is equal f a f dash ah plus absolute value of h epsilon h for all h belongs to b0 r, where f dash a is linear from Rn to Rm and epsilon h tends to 0 as h tends to 0. Now for k equal 1 to n, we have del f del k is equal limit t tends to 0 f a plus t e k minus f a t. So this is from the definitions of the differentiability of a function, and we have that this f dash a is linear from Rn to Rm, and this epsilon h will goes to 0 when absolute value of h tends to 0. Now we already formulated in previous lecture that partial derivative with respect to a variable xk can be written in this form. So we are going to use this to prove our theorem. So this formula is given in the previous lecture, slide number 6. Now this del f del xk, this is limit t tends to 0 f a plus t e k minus f a over t. So from the previous formula, this formula, we open it now. This we open it, and then we got it. This formula f a f dash a t e k plus epsilon over t e k epsilon t e k minus f a over t. So this f a and f a will cancel out. Then we will have here limit t tends to 0 t f dash a k over t plus limit t tends to 0 t e k epsilon t e k over t. So this terms we separate it. Okay, so now we'll see that how the limit will look like. So now from where this part is coming, t f dash a e k. So from here, how we can convert this is as t f dash a e k over t. So what we have, f dash a is linear from Rn to Rm. So therefore f dash a t e k. So this t can be taken out. So you will get it here t f dash a and operating on e k. So this is written from this ideology. Okay, so this t and t will cancel out, and then we have to try to check this, what is the limit. So to calculate the limit, we'll have here consider two cases. First, consider t is greater than 0. So therefore absolute value of t e k over t will goes to t absolute value of e k epsilon t e k over t. So now this t cancel out. Then we will have absolute value of e k epsilon t e k. Absolute value of e k, this will be actually 1. But we leave it here as absolute value e k. And this epsilon t Tek will tends to 0 as we shown with the conditions of the differentiability. So therefore, this whole limit is going to 0. Now next, we have here when t tends to 0 minus again. So absolute value of t will be minus t. So this t and t we cancel out, and we will have minus, and then with the same logic as previous, this will be 0. So therefore, overall, the limit is 0. And we'll have the partial derivative is f dash a, which is the part a. So therefore, partial derivative exists for all k is equal 1 to n. For the part b, let's for any h belongs to Rn, we have h is equal h1 is to hn. So this is h1, we can write it h1 1 dot dot 0 and then hn 0 1. So therefore, this one is actually e1, this is en. So we can write it like this, h1 e1 plus hn en. So this can be written as k equal 1 to n hk ek. So this form of h we are going to help to prove our theorem. So now the last part is that f dash a h. So this can be written as f dash a h is replaced by this form as proven in the previous slide. Now f is linear, so therefore we can move it inside. Sorry, f dash a is linear, so we can move it inside it, and hk can be taken out, so we can combine this part. Now f dash a ek from the first part can be written as the partial derivative with respect to x. So this proves the theorem. Now we have an example here. Let f r2 to r defined by fx is equal x y x square plus y square 0 and xy is not equal 0 0 and 0 when xy is equal 0 0. So now the question is here, find del f del x 0 0 del f del y 0 0. Second is f is continuous at 0 0, and third is f is differentiable at 0 0. So we are going to answer this question. So first we will calculate f del x. So part A here, del f del x, this is we can do two way. So it can be like this, del f x0, and at the point x is equal 0. But this is at x0, the function is still 0, so therefore the partial derivative will be 0. So this is one method, and another method 2, we can do like this, del f del x is equal limit h tends to 0, f of a 0 minus f of 0 0 over h. So this case also limit h tends to 0, 0 minus 0 over h is equal 0. So same way the del f del y at 0 0 is at 0 0. So this is equal del y f 0y at the point y is equal 0. But f0y is 0, so therefore we will get the derivative is 0. So therefore both partial derivative of f at 0, 0 exist. Now part B, to show the continuity, let one sequence an is equal 1 over n, 1 over n. Then limit n tends to infinity an is equal 0, 0. But f of 1 over n, 1 over n, this is equal xy. So it is 1 over n, 1 over n over 1 over n square plus 1 over n square. Here we will recall the functions f of xy is equal xy over x square plus y square. So this is equal 1 over n square over 2 over n square is equal half. So therefore an tends to 0 as n tends to infinity, but f of an does not tends to f of 0. So therefore f is not continuous. Now part C, since f is not continuous, it cannot be differentiable at a is equal 0, 0. Now remark, in this example, it shows that partial derivative does not depends on the continuity of the as here the partial derivative of 0, 0 exists, though the function is not continuous. 4.2, which is Jacobian matrix. So first we will define the Jacobian matrix. Let omega be open in Rn and A is a point in the omega. We define a functions f from omega to Rm. So the function is basically from Rn to Rm in such a way that it has x is from x1, x2, xn, because we have here from R n, and the function fx is equal, have a component up to m because it is on R m. So therefore we got the such functions with the partial differentiable at the point A. So this function f should be partially differentiable at the point A. Means all the first order partial derivative should exist. So since we have here n variable, x1, x2, xn, n variable, so we should have n partial derivative for the function f. If such condition satisfied, then we can define a matrix involving all these partial derivative, and we denote this is as JFA. So JFA here, the J is for Jacobian, F is for the functions, and at the point A. And this matrix will be given as like this. JFA will be, now just observe it, that what you have in the first row, all the cases, the function is F1. So it will be the derivative of the function component F1, okay, with respect to all the component. Then second row is for F2, and the last one will be Fm, and partial derivative with respect to all the variables. So what we are getting here, you will see the number of the rows will be F1, F2, Fm. So that is m number of rows. And how many columns? Columns is here x1, x2, xn. So therefore n column. So you are getting a matrix of Fm by, and this matrix is known as Jacobian matrix of F at the point A. So now we have a notes here that if F is from Rn to Rm, then the Jacobian matrix will be in the class of functions, a class of matrix m by n. Okay? So if you have F is from R3 to R2, then in this case JFA will be M2 by 3, means it will be 2 by 3 matrix. Okay, now let's have one example here. Here is that find JF1 minus 1 from FR2 to R3 defined by this f of xy equal ln 1 plus x square y square tan inverse xy and x plus y square. So we need to find the Jacobian at the point 1 and minus 1. So to do that, we will divide these functions in a component wise as per our requirement. So let's say a solution. So denote f1 xy is equal ln 1 plus x square plus y square. F2xy is equal tan inverse xy, and F3xy is equal x plus y square. Now we will calculate the partial derivative of each component at the point JF1, at the point 1 and minus 1, and with respect to both x and y. So del F1 del x at the point 1 minus 1. So this is equal del x. So since we are doing partial derivative with respect to x, so we will take the point 1 as x and fix y by minus 1 at the point x. This is equal del x of ln 2 plus x square at the point x is equal 1. So the derivative of this one will be 2x over 2 plus x square at the point x is equal 1. So this will be 2 over 3. So we got our first entry of the matrix is 2 by 3. So next we'll continue with the same way. So del f1 del y at the point 1 minus 1. So this is equal del y, and then we will have ln. So x is equal 1, we will put it. So 1 plus 2 plus 2 plus y square, and at the point y is equal minus 1. So this is equal 2y over 2 plus y square, so which is minus 2 over. So our next entry is minus 2 over 3. So in the next step, we are going to take the derivative of y2. So del f2 del x at the point 1 minus 1. So this is equal del x of tan inverse. So we put y equal minus 1. So this is tan inverse minus x at the point x is equal 1. So this is equal minus 1 over 1 plus x square at the point x is equal 1. So this is because ddx of tan inverse ax is equal 1 over a over 1 plus a square x square. So this will gives us minus 1 over 2. This is another entry of the matrix. Our next is similarly del f2 del y at 1 minus 1. So this is equal del y of tan inverse y at y equal minus 1. So this is equal 1 over 1 plus y square. So this is equal to 1 over 2. And this will be 1 over. Next, we will have del f del 3, which is very easy. Del f3 del x at the point 1 minus 1. So this is equal del x of, so our functions was here x plus y square. So this is x plus y square. So the y we can put it as 1. So x plus y at the point x is equal 1. So which is equal 1. So this is the entry of the matrix. The last one is del f3 del y at 1 minus 1. So this is equal del y, and x is 1, y square at the point y is equal minus 1. So this is equal 2y at the point y equal minus 1. So this is equal minus 2. This is another. So therefore, finally we have jf at the point 1 minus 1. So this is equal. I'll write the matrix and then we'll see that how it is coming. So it will be del f1, del x, del f1, del y, and of course at the point 1 minus 1, then del f2, del x at 1 minus 1, del f2, del y at 1 minus 1, del f3, del x at 1 minus 1, and del f3, del y at 1 minus 1. So we got all those values and we need to just write it here. So we'll go back and check what are the values. So we got 2 over 3 minus 2 over 3 minus half, half. 2 over 3 minus 2 over 3 minus half, half, and here we have 1 and minus 2. So note it here, f was from R2 to R3. So the expected matrix JF 1 minus 1 should be M from M in the class M3 by 2. So this matrix is 3 rows, 2 columns. So that's all. So now we have a theorem here. This theorem says that let omega be open in Rn and A belongs to omega. Then the functions f from omega to Rm is differentiable at A. This is given. That function is differentiable at the point A. So now let lambda belongs to R. Then we have f dash A. Okay, so derivative of this function, since it is differentiable, so derivative of this functions will be linear from Rn to Rm, and the matrix of f dash A is equal Jacobian of the functions at A. So the derivative functions, if you convert it to the matrix form, then it will be same as the Jacobian of the function f. Next is that this can be written as the functions f dash A operating on H belongs to Rn, is equal jfa dot H. So it will be, can be, means take the matrix and take the product of the matrix with the matrix H, then you will get same as the dot product of the functions. So this is the properties of Jacobian matrix, or this is the relations between the Jacobian matrix and the derivative of the function. We have another theorem, and this theorem says that let omega be open in Rn, then and A belongs to omega, the point. Then the function f and g both are from omega to Rm, differentiable at A, same is the same point. Then the Jacobian of that linear combinations of those functions f and lambda g is equal the Jacobian of f at the point A plus lambda Jacobian of g at the point A. Okay, so this can be proved by using the concept, basic concept of the differentiability. Now, next theorem is that if omega be open in Rn and A is a point in the omega, and let small omega be open in Rm, then the functions f from capital omega to small omega is differentiable at A, G is differentiable at f of A. So these are given conditions. Okay, so function f is from capital omega to small omega, G is from small omega to the set R is differentiable at f A. Then the Jacobian Jacobian of the composition function G composition f at the point A is equal Jacobian of G at the point Fa multiply Jacobian of f at the point A. So you have to understand here the Jacobian G will be defined on Fa. So if we draw a Venn diagram, so let's you have here the omega which is on Rn, then here you will go, it will be on Rm, there is a set small omega, and then from omega to Rs. So we have a function here, this f, and this is g. So therefore, if the point A is here, so this is the point A, then there will be a point f of A. So this function is going there. So this is by f, and from f A we have here this. So this is g. So this is g of f. So therefore Jacobian of this function, so it for the g, Jacobian for g will be defined in the point f A. Now we have an examples where we have to find the derivative of the composition, Jacobian of the composition function. So we have given function f is from R2 to R3, and this is defined like this: e to the power xy first component, x square y second, and x plus 2y third component. And g is from R3 to R2 defined by this cosine pi x and x e to the power y g. Then we have to calculate the Jacobian of the composition of these two functions at the point 1 and 0. Okay, so we recall from the previous theorem that Jacobian of this composition is Jacobian of Fa and then multiply with Jacobian of f at the point A. So first we calculate this Jacobian of f at the point 1, 0, and then we'll calculate Jacobian of g at the point f1, 0. So given that f R2 to R3 is defined like this, so we take the component of this function. F1 is e to the power xy, f2 is x square y, and f3 is x plus 2y. Then we calculate the partial derivative of each component. with respect to x and y. So f1 xy at the point 1 0. So again, by adopting the same method, we put y equals 0 and keep x as a variable, and then we are getting this one e to the power x0, which will be 1. So therefore partial derivative of 1 will be 0. So we got one entry is 0. We continue with this with respect to y and the component f1, and in this case we will keep x is the constant value and y is the variable, and then we got the derivative, and at the point y equals 0 the value is 1. So in this case matrix entry is 1. We continue on f2. So f2 1 0, so y equals 0, so it will become 0, the derivative is 0. Same way f2 with respect to y, and then we put x equal 1 and x equal 1 here and y as it is. So at the point y equals 0, so the partial derivative is 1. So at the value y equals 0, the derivative is also 1. And our last one is easy, f3x at 1 0 is equal derivative of x, which is 1. And then f3y, that's also 1 plus 2y, because we put here x is equal 1, y as it is. So therefore we take the partial derivative, and the derivative is 2 at the point 0, so the value is 2. So we got the matrix form for Jacobian matrix for the function f, which will be 0 1 0 1 and 1 2. It's clear. Again, check it. We have f is from R2 to R3. So the Jacobian f at any point 1 0, it will be 3 by 2. So our matrix here 3 by 2. So it's correct. Now we'll calculate the for the functions R3. G is from R3 to R2, and it's defined by this function. So again we'll consider two component of G. G1 is xyz equal cosine pi x, and G2 is x e to the power y and z. Then we also note that f10, because we have to calculate at G f10. So therefore we need to know what is the value of f10. So f10 from the previous functions, it will be 1 0 1. So we have to calculate the Jacobian for G at the point 1 0 1. So again we continue with the similar partial derivative, and so del G1 del x at f10. So this is the point, and it is the partial derivative of cosine pi x. So this one, and this will be minus pi sine pi x at x equal 1. So it will become sine pi, and sine pi will be 0. Then the second one is with respect to y. So when we take with respect to y, we have to put x is equal 1 here. So x is equal 1, y is as a variable, and g is equal 1. So there is no g in this case, no y. So therefore it will become cosine pi, and which is a constant with respect to y, so the derivative will be 0. Then here we have to do with respect to g also, and again like the y we have here, the derivative is equal 0. Now we'll calculate for G2. So G2 101 with respect to x. So if you keep x as the variable, so from here x is the variable, y is 0, z is equal 1. So it will become x e to the power 0 1, so which is nothing but the partial derivative with respect to x at x is equal 1. So this is equal. Next we will take with respect to y. Then again from this part we have x is 1, y as it is, and this is 1. So derivative of with respect to e to the power y. So y equals 0, and then it will become e to the power 0 is equal 1. And the last one is with respect to g, again with the repeating process, you will get del g derivative, and this is only g is equal 1. This is g is equal 1, and then you will get it, the derivative is equal 1. So we got now the matrix for Jacobian of g. So this is equal, we got this matrix, and the matrix is 0 0 0 1 1 1. Again we recall g is from R3 to R2. So the matrix Jacobian g, whatever the point it is, in this case f10, this will be 2 by next we'll have the finally we have the answer here. So Jacobian of g composition f at the point 1 0, not f10, at the point 1 0, which will be the Jacobian of g at the point f10 and Jacobian of f at the point 1 0, and then we got the matrix. So this is, we got this matrix 2 by 3, this is 2 by 3, and this is 3 by 2. So product is well defined, and if we take the product we will get 2 by 2 matrix 0 0 1, and this is the Jacobian of g composition f at the point 1. Okay, now we have a definitions here. It is function of type C1. Okay, in this definition, so let omega be open in Rn, and we have a function f, we denote it as C1 omega, which means that f is a C1 type function if f is partial differentiable at all points on omega. So that means any first order derivative with respect to all the derivative, or with respect to all the variables that exist at any point. And this all the first order partial derivative, which we denote as del f del xi, and I is 1 to n, are continuous on omega. So two condition is there, which it should be differentiable at all point in the on omega, and should the all the partial derivatives should be continuous. Then we call that function as a type C1. Now we have a theorem is that it gives a relation between the functions f C1 omega. Is type C1 function is how it's related with the derivative. So it says that if f is on C1 omega, then it is differentiable on omega. And from a previous theorem we have that if it is differentiable, then we can always like this. Okay, so which will be can be later, means we can say that from the previous one theorem. So this is Jacobian of f at the point A, okay, dot h. Okay, now we have a problem here that prove that f R3 to R defined by f xyz is equal 1 over square root of 1 plus 4x square plus y square plus z square is differentiable on R3, and we have to find the derivative of this function. So this means that if we are able to show that this function is a C1 type, then it is enough to conclude from the previous theorem that it is a differentiable function and we can calculate the derivative. So first we'll show it, calculate the partial derivative of this function. So del f del x. So this is equal del x of 1 plus 4x square plus y square plus z square to the power minus half. So by the rules of the partial derivative, we'll get it here. This is equal minus half 1 plus 4x square plus y square plus z square minus 3 over 2, and the derivative of 4x square will be, so partial derivative of 4x square, so which is 8x. So we can simplify it, 1 over 2 1 plus 4x square plus y square plus z square to the power 3 over 2, and this will be 8x. So this will be minus 4x over 1 plus 4x square plus y square plus z square to the power 3 over 2. And we can see that this is a continuous function. Okay, because on R3, so this function is always defined because already square root of 1 plus 4x square plus y square z square is defined. So denominator never be 0, and numerator we have only 4x, which is a polynomial kind of the thing. So it's a rational functions where the denominator never be 0. So it's continuous. So in similar way, we'll calculate similarly del f del y. So this will be minus y squared. So derivative of y squared is 2y. So it will be, we can write it directly. So the first part will be same. So this is 1 over 2, 1 plus 4x squared plus y squared plus z squared, and then we will have a partial derivative of y squared. So this is equal minus y over, this is 3 over, minus y over 1 plus 4x square plus y square z square over 3 over 2, which is again a continuous function. So then we have here last one, del f del g. So this is equal minus 1 over 2 1 plus 4x square y square z square to the power 3 over 2, and then derivative 2z. So this is equal minus z over 1 plus 4x square y square z square to the power 3 over, again it is continuous. So therefore del f del x del f del y del f del z exist on R3, and all of them are continuous. So therefore, by the theorem here, that if f belongs to C1, then it will be differentiable, and the differentiability can be calculated
by this formula. So therefore we get it here. So therefore F is belongs to C1 R3, and by theorem previous slide, we have F is differentiable on omega, and F dash, now for H1, H2, H3 belongs to R3, F dash X H. So this is equal H. F dash XH is equal H1 del F del X, here is XYG, plus H2 del F del Y plus H3 del F del Z. So this is equal, we will have here already calculate. So this is equal minus 4x. So we'll write it together. So this will be minus 1 over 1 plus 4x square plus y square plus z square to the power 3 over 2, and then you will get it here 4x h1 plus y h2 plus z h3. So this is the answer. Here we are going to discuss about the directional derivative. We start with the definition of the directional derivative. So for that we need an open set omega on Rn and a point A in the omega, and f is a function from omega to Rm, and v belongs to Rn is a vector in which directions we are going to define the directional derivative. So we say that f has a directional derivative at A with respect to the vector v if the limit t tends to 0, f a plus tv minus f a over t exists. So if this limit exists, then we have a directional derivative of the function f along at the point A along the vector v, and the value of this limit is the value of the directional derivative. Now the notation for this generally use dvfa. So that is directional derivative of f at the point A along the direction of v, and this is equal the limit if the limit exists. Now in particular, if we take v is equal ek, so v is equal ek, while ek means 0, 0, 1, 0, 0. So kth vector is, kth component is 1. Then this directional derivative is same as the partial derivative of f with respect to the variable xk. So if you take e1, that means 1, 0, 0, then d e1 fa is equal del f del x1 a, where f is a function, means whenever you have the f is a function x1, x2, xn, and then we will have here the component, we can say, so this is, we say x, we take this is x, so it will have fx, f2 x, and then fm x. So we are taking the partial derivative of f with respect to the variable, x1. Okay, so if it is e1, so same way e2 will be the partial derivative with respect to x2, and so on. So this gives us a relation between the partial derivative and the directional derivative. Now we have a theorem with associate with the directional derivative. So this theorem says that let omega be open on Rn. A is a point in the omega and f from omega to Rn. Now if f is differentiable, so this is the condition that if f is differentiable at A, then for any v belongs to Rn, directional derivative exists, and the directional derivative at A is associated with the derivative of f with this relation. Okay. So therefore differentiability implies the directional derivatives, but the opposite is not true. Hence, a particular direction's derivative does not guarantee that function is differentiable in the whole all directions and is differentiable at the point A. So the opposition is not true. So differentiability guaranteed that there will be a directional derivative at that point in any direction of the vector v, but the opposition is not true. Okay, so we'll do the numerical problem to calculate the directional derivative and all those related use of the theorems and definitions in the end of this chapter, means in the next lecture. Okay, now we move to the next topic, section 4.4, which is mixed partial derivative. So we have the partial derivative till now is del f, del x, del f, del y if two variable functions, and so on. Or if you have del 2f, del x2, del 2f, del y2, second order partial derivative. Now the question is, we will have the mixed partial derivative del f, del x, del x, del y, means one time with respect to y, another time with respect to x. Or we will also discuss if it is opposite, then how they are connected. So this is called the mixed partial derivative. So let's start with the definition. So it is the same way that omega is open on Rn, A is a point in the omega, and f is a function, and then we say that del 2f del xk del xi. So this is a mixed derivative with respect to the variable xk and with respect to the variable xi. Exist if del f del I exists for all xi, and del f del xi is partially differentiable with respect to xk at A. So first we'll calculate del f del xi. So it must exist. Okay, and then whatever the new functions will come with respect to all the variables from x1 to xn, then the new function is also be differentiable with respect to the partially differentiable with respect to xk at A, then the mixed partial derivative will exist. Okay, so we can say that this can be written is like this: del 2f del xk del xi operating on A is equal. First we'll calculate the partial derivative of f with respect to xi. Then we'll take the partial, we'll get the new function, and then we'll take the partial derivative of the new functions with respect to the variable xk, and then put the value of the point a and calculate the value of the function derivative. Okay, so if it is opposite xi xk, then you have to take the first with respect to xk and then with respect to xi. Now the natural question is this: are they always equal? The answer is no. They may not be always equal. Okay, now we have a function here. Then it says that the function is from R3 to R, defined as ln 1 plus x square z square plus y square, and we have to find del 2f del z del x at the point 1, 0, 2. So first we ignore the point and we calculate it the derivative, and we'll see that how it will come. You cannot use that earlier definition that we will take the all the point. For example, we are taking first partial derivative with respect to x, so we just substitute the other variables value and only keep x, then you will get the derivative. So that will be not possible here, because we have to do first all the derivative and then we have to apply the point here. So we will calculate it in this way. Solution. So first we need to calculate del f del x. This is equal. So derivative of ln 1 plus x square z square plus y square. So we know that we'll use the chain rule. Derivative of the ln will be 1 over 1 plus x square z square plus y square, and then partial derivative of the inside variable. Now when we do the partial derivative with respect to x, other will be constant. So therefore we will have this is 0. This is only you have 2x z square and this is 0. So we will get it here 2x z square over 1 plus x square z square plus y square. Now we will take the partial derivative of these functions with respect to g. So next is del z del f del x. So this is equal del z, and we have here 2x z square plus 1 plus x square z square plus y square. So this is del f del z. Now since this is the last step, so we can use this point. So you have to do it at 102. So this can be done as, so we can put the value of x and y and keep z as it is. So therefore we'll get it here. X is 1. So this will be 2 z square over 1. X square is 1. So it is z square. Y is 0. So this is like this at the point now z is equal to. So therefore we get the derivative. What will be the derivative here? 1 plus z square whole square. To add is like this. So this is 2z, and then 1 plus z square minus, then we'll have here 2 z to the power 3 at z is equal So we substitute the value 2, and this will be 2 multiplied 2, 1 plus 2 square minus 2, 2 to the power 3, 1 plus 2 square whole square. So this is equal to, and then it is 4 and this is 5, 20 minus this is 2 and 8, 16, and denominator is 4 plus 1, 5, 25. So this is equal 20 minus 16, 4, 8, 8 over 25. So here you can, in this part, without substituting these points, you can calculate all the partial derivative, and then also you can substitute it in the end, and you will get the same answer. So the answer is 8 over 15. Okay, now we have here one definition is about the function is type Cn. Okay, and on omega or f belongs to Cn omega, where n is the natural number including infinity. We can say extended set of natural number, and this is the f type of Cn. We already defined C1. C1 means all the first order partial derivatives should be continuous. Now naturally the Cn will be all the nth partial derivatives should be continuous. Now when we talk about the nth partial derivative, then it will come to the mixed derivative also. So this definition is that if all the partial derivative of f of order less or equal to n are continuous. So when we say that C2, okay, and let's say, so f belongs to C2, this means all the partial derivative of f of order 2 or less are continuous. Means first order and second order partial derivative should be continuous. Now if f is a two variable function, so we will have del f, del x, del f, del y, del 2f, del x2, second order partial derivative, del 2f, del y2, and del 2f, del x, del y, del 2f, del y, del x. All these should be continuous. Then we can say f is belongs to C2. Okay, so therefore, with this continuations means C0 means function should be continuous. C1, the first order partial derivative continuous. C2, all the second order partial derivative continuous, and so on. So C infinity will be all kind of the partial derivative should be continuous. So therefore, this is the smallest set. Okay, how much conditions will increase? That will be the smallest set. So C naught is function is continuous only. C infinity is all kind of the partial derivative of any order should be continuous. So this is the smallest set. Okay, now if we have a f belongs to C to infinity, and if the function is C to infinity, then the partial derivative, second order partial derivative with respect to two variables are equal. So therefore, if f belongs to C2 and f is a function of two variable xy, then del 2f, then del 2f, del x, del y will be del 2f, del y, del x, means for that function should be belongs to C to infinity. So if belongs to C to infinity, then they are equal. And this theorem is known as the source theorem. Okay, so now we'll come to the next topic. Is theoretically this is the last topic, 4.5, which is the gradient of a function. So we'll again start with the definition. So gradient of a real function, sigma be open on Rn, f is from sigma to R, a differentiable function. So we are starting with the condition that function is differentiable at A. And f dash A is linear from Rn to R. So here the function is from omega to R, not Rn to Rm. It is Rn to R. So therefore, the derivative is belongs to in the set of linear Rn to R. Then for from this theorem, we did it in chapter 1, there exists a unit vector. There exists a unit vector gradient. This is notation is gradient of fa belongs to Rn, such that for all h belongs to Rn, FAH is equal gradient of FAH. The gradient of FA is the notation. This gradient of FA is the gradient of F at A. Now we have a theorem here that omega be open on Rn. F is a differentiable function at A belongs to. Then gradient of Fa is calculated by like this. I think there is a, this is f dash ah is equal gradient of f a h. This theorem we are not going to prove it. So the gradient of fa is the partial derivative of f with respect to the each variable is known as the gradient of fa. Okay, now we have an example here. Let f is from Rn to R, defined as fx is equal absolute value of x whole square. Then the question is find gradient of fx for all x belongs to Rn. There are two methods to solve it with respect to the previous theorem. We can connect it with the gradient of means fa or fx with the derivative, or we can calculate directly using the partial derivative of f with respect to each variable. Solution here, so for all x belongs to Rn, because the function is defined on the Rn, we have fx is equal absolute value of x. So what is x? X is x1, x2, xn. The absolute value of x whole square, this will be x1 square plus x2 square plus xn square. Now if we take the partial derivative of f with respect to all variable, then it will be we can get the gradient. So here is f is kind of polynomial, so it is differentiable. And then from the previous theorem, gradient of fx is equal del fx del x1 and this fxn. So each cases, if you take the partial derivative with respect to x here, with respect to each variable, so you will get it 2x1, 2x2, 2xn. So if you take out 2, so it will be this is equal to x. So gradient of f is equal to. You can solve this one by using a chapter 3, where we will get the derivative. So if you solve it like this, so it will be f dash x h is equal to x dot h. So from the definitions we will have that this is equal gradient of fx dot h is equal to x dot h. So comparing this, we'll get it gradient of fx is equal to x. So this way also you can show it, but for that you have to show that calculate the derivative using the definition of the derivative. Then you can apply this theorem. So this is, we can say, method 2, but this is the method 1, which is the easy method. The last part of this chapter or this module, and in this part we are going to solve examples based on the whole chapter 4. So we have our first example here, where we have given a functions f from R2 to R, which is defined by in two part, with when the point is not equal 0 0, means except origin. This is given by these expressions, and the case of at origin at 0 0, the function is 0. So we have to prove that that f is continuous at 0 0, and then we have to find the existence of the directional derivative at 0 0 for any direction of a vector v, and then conclude that f is not differentiable at 0 0. So it is continuous but not differentiable. Okay, so let's start. Okay, so first that we have to show that f is continuous at 0 0, and we are going to prove it by showing that absolute value of f of xy minus f of 0 0 is less than equal gxy, where gxy is a function of xy such that it will tends to 0 when xy tends to 0 0. So if we are able to prove that, then this is equivalent to say that limit of f of xy at 0 0 is equal f of 0 0. So that means f is continuous. Okay, so first we recall the function here uh, from the previous slide. So we have given function is this one, and then we are going to apply this equation. So this will gives you here f of xy minus f of 0 0. So f of xy is this one, and f of 0 0 is 0. So now we are going to simplify it and so that how we can write it. So this can be written as y e to the power y, and y square over x square plus 3y square. So why we are taking this one? So from, and how we are taking this one? So from this part, y to the power 3, we kept y square, and remaining y and e to the power y separately, and here y square plus 3y square. So now why we write it like this is because the fact that y square over x square plus 3y square. So which whatever may be the y is positive, negative. So this can be written as 1 over 3, which is less than 1. So we are using this concept. Then from that we are getting here this is less than equal y e to the power y. In fact, it is not less than equal, it is strictly less than. So it is less than y e to the power y. So now this we are taking as the function of g xy to fulfill the requirement of this one. So take gxy equal y to the power y, absolute value, and then clearly gxy is going to 0. Gxy is going to 0 as xy tends to 0 0. So therefore we fulfill the conditions, this one. So this implies that f is continuous at 0 0. Now come to the second part. but we have to study the existence of the directional derivatives at 0. So for that, what we'll do, we are considering one vector v, v1, v2, r2 except 0, 0. So any vector is there. Now we are going to find the means direction derivative in the direction of v. Okay. So the definitions, we recall the definitions here. The definition of direction derivative. So dvf 0 will be given as limit t tends to 0 f at the point where we are calculating the direction derivative plus t along the vectors v, that is v1 v2 minus f of 0 0. So if we simplify it, so you will get it here f of t v1 t v2 minus f of 0 0 over t. So we recall the function, we recall the function here f xy equal y to the power 3 e to the power y x square plus 3y square. So from that we are substituting here this one from this part. So you will get it, this expression, and f of 0 0 is 0 and divided by t. So therefore if you simplify it, so you will see here t square and t to the power 3, that's will go on t, and this t and that t cancel out. So we left with this part, and then v1 square plus 3 v2 square. So since it is e to the power t v2, and when t tends to 0, so this will be 1. So therefore you will get the limit v2 to the power 3 over v1 square plus 3 v2 square. So since v1 and v2 are togetherly cannot be 0, so therefore this limit exists and we have the directional derivative. Now, the third part is that conclude that f is not differentiable at 0, 0. For that, we assume this, we'll show it by the contradiction. So we assume that f is differentiable at 0, 0. So since it is differentiable, then for any v, the directional derivative exists, and the directional derivative is related with the derivative of the vector function like this relation. So it is equal f dash 0 0 phi. Now we already calculate the directional derivative of this, and now we are going to calculate this one, and we compare them, and we'll see that what is the contradiction. So now the derivative of this can be calculated as df dx 0 0 v1 plus del f del y 0 0 at v2. Okay, so this is the relation between the derivative and the vector. So then from part B we have here that directional derivative of f00 is v2 to the power 3 v1 square plus 3 v2 square, for v is equal v1 and v2. So is equal e1 10, then this is equal to the partial derivative of f along the direction x, so which is equal to de1 f00. So in this case means v1 is 1, so this means v1 is equal 1 and v2 is equal 0, and if you substitute it here, so you will get it the value 0. So therefore the partial derivative at partial derivative of f with respect to x at the point 0 0 is 0. Same way, if we take e2, b is equal e2 0 1, in this case we will have here v1 is equal 0, v2 is equal 1. So again, from this relation we get it that from here we get it that the partial derivative of f with respect to y at 0 0 is equal 1 over 3. So we got the relation here. So therefore from this relation again come back to this, so you will get it. Then from the previous part we will have here v2 to the power 3 and v1 square plus 3 v2 square is equal to 1 over 3 v2. So now if you simplify it, then you will get it v1 square multiply v2 is equal 0. How it is? So if you cross multiply it, you will get it 3 v2 to the power 3 is equal v1 square v2 plus this 3 v2 to the power. So this 2 cancel out and you get it here. You get it here. This implies v1 square v2 is equal 0. So now this is possible because v1 and v2 are togetherly cannot be 0. So therefore this is possible. Either v1 is or v2 is 0. Okay. Now in the case of v1 and v2 are non-zero, both are non-zero. So let's say v is equal to 1 1. Then what will happen? Then from this relation we get it then we have this implies, so this relation implies that 1 over 4 is equal 1 over 3, which is a contradiction, not possible. So therefore our assumptions that the function is differentiable is wrong. So we got the conclusion that function is not differentiable at 0 0 1. Now we move to the example 2, and here it is similar kind of the function we have. So this is the expression when xy is not equal 0 0 and 0 when xy is equal 0 0. Again we have to show that f is continuous, and then we have to discuss the existence of partial derivative at 0. So let's so the first part, the continuity will prove it in the same way as in the previous example with this by showing that g and gxy tends to 0 0 as xy tends to 0. So again just recall the function. So function is f of xy minus f of 0 0. It will be like this. So again with the same logic we can say that this is yx and this, so this is actually less than yx. So again by the same logic as we saw in the previous, so y square over x square plus 2y square, which is less than equal half and less than 1. Okay, so we'll take this as a g. So gxy equal yx. Then we'll see that gxy is tends to 0 as xy tends to 0 0. And from there we'll say that f is continuous at 0 0. Okay. Now we'll see the study the existence of the directional derivative at 0 0. For that we consider the the point vector v is equal v1 v2. So for that we consider the vector v is equal v1 v2 belongs to R2 minus 0 0. Then using the definition of the directional derivative we will have now from the function f we substitute here. So we'll see that here t to the power 3 and t, so it will be t to the power 4, and this is t square and there is t, so it will become t to the power 3. So it, after simplifications, you will get this form. Then this t and t to the power 4 over t to the power 3, this is t. Since t tends to 0, it will become 0. So therefore, the direction derivative is 0 along any direction. The direction derivative is 0. So therefore, the partial derivative exists and it will be 0. So for that, we will take it here that for v dv is equal 0, and in particular, if we take v is equal u1, then you will get the partial derivative with respect to x is 0, and then if you take v is equal e2, and then you will get the partial derivative with respect to y is 0. So therefore, the first order partial derivative of exists at 0, 0. So this is the conclusion. Okay, now we have an examples. Here again, we are taking the functions from R3 to R, and we are going to discuss the continuity of f. And then again, we are going to discuss the existence of the partial derivative at 0. Okay, here you have to note that we are going to discuss the continuity of f at 0, 0, 0. So it does not, like the previous question, it is not guaranteed that function is continuous or not. Okay, so we will see that here that it is a continuous or not. We want to going to discuss it here. So here we will take it with respect to the first we will discuss about the continuity. Is it continuous or not? So we took this a sequence a n is equal 1 over n, 1 over n, 1 over n on R3. And then clearly we'll see that a n tends to a0, 0, 0, 0 as n tends to infinity. So which is clear from this, because 1 over n tends to 0 when n tends to infinity. So now we are checking that where f of a n is going. Is f of a n will go to f of a0 or not? So here we'll see that f of a n, which is equivalent to f of 1 over n, 1 over n, 1 over n. So now from the given functions, we have here this expression. So you will see that after simplifications, we are getting it 3 over 4. But it's given that f of 0, 0, 0 is equal 0. So therefore, this is not equal f of 0, 0, 0. So but here a naught is 0, 0, 0. So this will gives us to conclude that a n tends to a0, but f of a n does not tend to f of a0. And hence f is not continuous at 0, 0, 0. So function is not continuous. So again we consider now three component vector v1, v2 and v3. Then by definition we'll have this expression. So we substitute it and we'll see that here this is become like this. Now here t square it will go on. This t square will cancel out. So we have an expression in this form 1 over t. So which does not exist when t tends to 0. The limit does not exist. So therefore, first order partial derivative of does not exist at 0, 0. Okay, now we have an interesting example here. So in this example, we have a linear transformation or linear functions from Rn to Rm, and B is a vector in Rm, and we consider a function f R3 to R. Sorry, this is Rn to R defined by f of x is equal half ax minus b whole square. Here x belongs to Rn. Now we have to so that f is differentiable and we have to find f dash x. We have to conclude that gradient of f can be written as in the matrix form with this A transpose, the matrix of linear function A, its transpose, then Ax minus. In particular, if A, X and B is given, then what is the value of gradient of f? So this thing we have to calculate. So first we'll show that f is differentiable, though it is proved in module 3, but we will revisit it and we will prove it again. And then we will find the f dash x. So part B is depend on part A. So let's have the solution here. So we recall the definitions of the differentiability. So for that we will write f x plus h is equal f of x plus th plus epsilon h, absolute value of h, where t is linear and epsilon h tends to 0 as absolute value of h tends to 0. Is and for h belongs to Rn, f dash x h is equal th. So from this we will have in this case f of x plus h, which is half of mod of ax plus h minus b whole square. So this is equal half ax minus b whole square plus th plus epsilon h, absolute value of h. So we'll classify the th and epsilon h simplification. So this is equal to half. So now we can write it this a plus b whole square. So this is ax minus b plus ah whole square. This is equal half ax minus b whole square plus th plus epsilon h mod h. So from this we will have here the absolute value. We will open it. So this will be half and absolute value of ax minus b whole square plus this will be ax minus b dot ah plus half ah whole square. So this is equal half ax minus b whole square plus th plus epsilon h, absolute value h. So if you compare this, you will get it. So this will cancel out with this term. And then we will get a relation here. This one will be with th and this one with epsilon h, absolute value of h. So therefore we get it here. th is equal ax minus B dot AH, and epsilon H is equal half AH whole square over absolute value of H. So this we already saw linear. So this is linear, and this is tends to 0 as H tends to 0. So this is uh, already shown in some video previous lecture. So I'm not going to prove it. So just we are going to take that. With this it will be the derivative. So therefore f dash x h is equal ax minus b dot ah. Okay, so using that previous definitions, we are going to conclude that gradient of fx is equal this one. So from the previous part, so we got f dash x h is equal th, which is equal ax minus b dot ah. So we know that f dash xh is equivalent to gradient of f of x dot h. So this is equal a star ax minus b dot h, and a star is adjoint of a, okay, which is defined as ax dot y is equal x dot a star y. So using these properties, we can write it this one in this form. So therefore, by comparing, we have gradient of f of x is equal a star ax minus b. Now the matrix of is known that matrix of a star is equal A transpose. So therefore, in terms of the matrix, gradient of fx is equal A transpose, then matrix A x minus B. Okay, so now next part is if is this is the relation, then what will be the this gradient of f? So last question is the gradient of f in case of a is equal like this. So therefore we will recall from part B that gradient of f of x is equal matrix A transpose and then matrix A x minus matrix B. So A transpose, in this case it will be 1 2 3 and then 0 minus 1 2, and then matrix AX, so operating on 1 0 2 minus 1 3 2, operating on minus 1 2 minus B matrix 1 0 2. So this is equal 1 2 3 0 minus 1 2 and then simplify it. So what it will be, this is minus 1, this is minus 2, so minus 4, it's minus 3 plus 4, so which is 1, minus 1, 0, 2. So this is equal 1, 2, 3, 0, minus 1, 2, and then if we simplify it, so this will become minus 2, minus 4, minus 1. Multiply it, you will get it here, minus 2, minus 8, and minus 3, and this one will be 0, plus 4, minus 2. This is equal minus 13, and this is 2. So the gradient of f at the point x is equal minus 13 over minus 13, 2. So therefore, gradient of f at minus 1, 2 is equal minus 13